Have you ever asked yourself how a robot makes a decision how to go from its current location to a target location? Then this lecture is for you, because we will discuss motion planning for mobile robots. So how do robots make decisions where to navigate in order to reach a target location? So typically a robot knows where it is, it knows where it should go to, it has a map of the environment and knows something about its own shape or own body form, so that it knows how it can execute local motion commands such as go a meter forward, and that the system will execute that without bumping into walls next to the robot, for example. And then a motion planning algorithm generates a sequence of motion commands or a sequence of states that the robot needs to visit in order to reach the target location. And it can do so in an optimal fashion. Optimal fashion means there's no better way for doing this in terms of the output result. So there's no better trajectory than the trajectory that the algorithm actually proposes. And of course, this optimality, as always, comes with some assumptions, such as which stage can we visit, do we discretize our space? But that's something that we're going to explore in this lecture today. So typically we are interested in computing a path or a trajectory which guides the robot on its fastest route to its goal location. And that's what we are going to discuss today. How do we make this decision where to navigate in order to reach our goal? So that can be a robot such as the one shown here on that slide, which navigates through the catacombs under Rome and needs to reach a certain location in those catacombs, but can be also any other type of robot, or even yourself. If you use your sat-nav system in the car and the system tells you where to navigate, you can do this with an algorithm called a star. Even though in devices used today, there may be some more advanced or optimized algorithms for the problem at hand, but the basic motion planning algorithm that underlies this can be solved with an A-star algorithm. So more concretely, we are looking today into robot motion planning using the A-star algorithm and discuss what A-star means, how it works, and how we can use this algorithm in order to build real robots that navigate through the world. So the motion planning problem is a standard problem in robotics since its beginnings. So there's a famous quote made by Uninformed in 1991, which states that motion planning is an essential task that robots need to do, because in order to do something useful, most of the robotic systems, or at least of the mobile robotic systems, need to move through the environment from A to B in order to succeed, in order to fulfill its task. So moving through the environment is a core ingredient of most robotic systems today, and therefore motion planning or path planning is an important capability for those systems. If we look to the, let's call it, classical motion planning and what are the traditional goals that we always look into, so the first thing we want to ensure is that the robot never collides with an object. So if we have walls or doors in the environment, we want to make sure the robot will never bump into a wall, always fit through the door frame without touching on the right or on the left hand side the door frame, or collide with a door or any other object in the space. So a collision-free trajectory is a requirement that we typically have. And among this set of collision-free trajectories from a start location to a goal location, we are typically interested in finding the trajectory which guides the robots on the shortest path, or that the robot can reach its target location as quickly as possible. So the shortest path is not always the fastest path. So there can be trajectories along which are longer, but along which you can drive faster. So you may take a small detour into account if you can drive faster on that trajectory. It's similar to you when you're sitting in your car and there are two roads you can take. The one is a highway and the other one is a local street through the city. Even though the trajectory along the highway is somewhat longer, you can drive faster on that highway and therefore will reach your target location faster. So for several applications, we are interested in the fastest route, but there are also applications where we may be interested in the shortest path. Often they are similar, but not necessarily the same. So the traditional goal in robot motion planning is provide a collision-free trajectory that allows us to reach the goal as quickly as possible. This is often formulated in static worlds. That means the robot knows about the world and also knows that the world does not change. That means there are no dynamic obstacles around. There are no humans moving around, no other traffic participants, for example. So this is something which is a very strong assumption and typically not justified in the real world. So whenever we go to real-world robotics, we need to take dynamic environments into account. That means environments that change while the robot is operating in this environment. These can be quickly moving obstacles like other traffic participants, but this could also mean that there are objects which are placed in the environment that hadn't been around when the robot was building its map, for example, or just data that's not stored in the map in general. And how can we deal with this? So how can we still navigate in an efficient or effectively, so have an efficient algorithm that computes a path quickly and get out a path which guides us to the target location as quickly as possible, and that we can still give some guarantees, at least guarantees under some assumptions, that the robot will not bump into an object, even as an object it didn't know before. In order to do that, of course, we typically need to make some assumptions how objects move through the environment. If the object is much faster than the robot, it basically chases the robot. Of course, this can lead to a collision we cannot avoid. But if we make certain assumptions about the movements of the other objects in the environment, we can make certain statements, at least probabilistic statements, if this trajectory will lead to collision, yes or no. So we are interested in finding trajectories that are reliable and that we can efficiently navigate on. And there have been a lot of techniques proposed in order to deal with those dynamic environments. Often we have to distinguish two things in here: a core planning algorithm that plans a general path from A to B, and then what we call like a local collision avoidance system that tries to follow that path but is allowed to deviate from the path in order to avoid collisions. And prominent examples are the dynamic window approaches, which are techniques which basically take into account which changes in the velocities the system can do, and this generates you a local window of states that you can reach. And then the question is which is the best velocity to choose in that window. You're basically choosing the velocity commands that bring you closer to the goal or along the trajectory towards the goal. And there's a large series of other approaches, some, for example, optimized for very confined spaces, so where it's very hard for the robot to navigate. Others more optimized through environments where you can go as fast as possible and can make smooth avoidance maneuvers around objects in the world, or that make some assumptions regarding optimal or near optimal behavior while navigating through the environment. So it depends a little bit on the approach that you want to do and the goals and your environment that you're in. So we will be looking today, especially here, into the so-called A-star algorithm, which is a very popular search algorithm, a so-called informed search algorithm that is used for a large variety of different planning problems, not only in robotics. It has been developed for robotics and is, again, one of the key AI techniques that we use today, that we find today in a lot of applications, and it's kind of the gold standard planning method. So it's kind of important to understand how that approach works, because it allows you to generate a sequence of states that you need to visit to go from a start to a goal location, and it does so in a very effective manner. There are again extensions and variants of the A-star algorithm, such as ARA-star, anytime real-time A-star, for example, which is a real-time algorithm that takes the computational resources, or an anytime algorithm, sorry, that takes the computational resources into account in order to optimize the trajectory, but guarantees, or not guarantees, but in most of the settings comes up with an initial trajectory very quickly, so that you can start navigating on and then optimize this trajectory on the way. Or the D-star family of algorithms, which can be used if you do a lot of replanning. So if you don't do a plan just once, but replan while the environment is changing, and then they allow you for substantially more efficient updates. And then there are also other approaches like Markov decision processes, which you then need to take into account if the uncertainty in your motion execution plays an important role. So if you assume the system can actually execute what it wants to execute, then you're typically fine with your A-star algorithm. But if you have uncertainties in your motion execution, you have to go for other things, other techniques, such as MDPs, for example. So let's have a look. What are the key challenges today in motion planning? So what the key challenges are, we want to find an optimal path. Optimal means under the cost functions that I'm providing. This can be shortest path, shortest collision-free path, fastest path, a path or trajectory which minimizes certain accelerations that occur that are very pleasant for humans. If humans are driven by the autonomous vehicle, like an autonomous car, you just want to have the fastest trajectory. You want to have also a trajectory which is, for example, legal, or a trajectory that is very convenient to when you're sitting in the car and you don't care if you arrive at the goal 2 or 3 seconds slower, as long as your ride is more pleasant, for example. So there may be different cost functions that you want to take into account. Here in this lecture, we are basically looking into the shortest path or the fastest path. Then the second question is, do you need to take into account uncertainties? These can be uncertainties in the action execution. So when you want to go from A to B and you give a command to the system, is the command actually being executed or is something else executed? So for example, if you say go a meter forward and the system goes only 95 centimeters forward, is this been taken into account? Is this actually a problem for you? So this is something that needs to be considered, and you may also take into account uncertainties in your perception system, that your perception system is not perfect. The other question is, how can you quickly react to unforeseen obstacle? So if a new obstacle is in your path, something that you were not aware of, how quickly can you react to these unforeseen obstacles? Or what happens if other traffic participants are moving through the environment and may collide with you even if you would stop? So these are things that your planning system may take into account, but that somehow depends on the application you're actually targeting. If we look into most robotics navigation stacks, we can see a so-called layered architecture. So you have different layers of planning until control algorithms which are executed by the system, running at different frequencies and having different tasks that the system is going to do. So what you can see here is a classical three-layered architecture. On the highest level, you have your planning algorithm. So that's something that we are starting with here with our A-star algorithm. So how to use a map of the environment and the information where you are in the world in order to plan a path that guides the robot to its target location. Maybe you do that once per second or once every 5 seconds or maybe 3 times per second. So, but at a rather low frequency. You're basically revising your plan based on the new estimates where you are in the environment and what happens around you. And then you typically communicate a sub-goal, so a sub-goal, let's say 5 meters in front of a robot, to a local planning system, a collision avoidance system. And the collision avoidance system runs at a much higher frequency, typically at the frame rate of your sensor. So this can be something from 5 Hertz to 30 Hertz or 50 Hertz maybe even, checking if there is an obstacle that moves near the path that the system wants to execute so that there's a risk for a collision. And if it sees that there's a risk that the robot would collide with an obstacle, it plans or varies the trajectory and generates alternative trajectories that the system then picks in order to avoid a collision. That's something that we often refer to as a collision avoidance system or a local planner. And then this collision avoidance system actually generates typically a motion command or a transition to a next state, and then you have a local controller that turns this local information into an actual steering command or control the motors of the vehicle so that the vehicle actually executes the path that, or the motion command it should execute. And typically there's also a correcting control loop that, for example, odometers are taken into account, so a sensor that counts the revolution of the wheels in order to make sure the platform actually executes what it should execute and takes some corrective actions. So today we will be looking more on that planning side, looking a little bit also into collision avoidance or a system which solves these two tasks jointly. Control is something that we cover in this course, but not in this lecture here today. So let's look into the standard motion planning problem or planning problem starting here from the top. If we look into the standard motion planning problem, we typically have as our inputs a start pose or start configuration where the robot is right now. It doesn't necessarily only has to be a pose. It could also be, again, a full state. If velocities, for example, matter and you start with a given velocity, you may want to take that into account as well. And then there is a goal configuration, like you need to end up at a certain location with a certain velocity, or I don't care about the velocity as long as you reach a certain XY configuration as fast as possible. So different ways for defining the goal state. It may also not just be one state, could also be multiple states. And then you need a description of the robot. Often it's a geometric description in order to understand what's the size of the robot, in order to check or combine this with the representation of the environment in order to identify the valid states, so states which don't generate a collision with the environment or with other objects around. So you typically need to have some description of the robot and some description of the environment or representation of the environment so that you can do these collision checks and in order to know what's free space, what's occupied space. And given that you have that information, the planning algorithm should turn this input information into the output information, and the output is the path, typically the shortest path or the optimal path or minimum cost path. Let's maybe be a bit more general, minimum cost path, and you define the cost function beforehand, that moves the robot from a start configuration to a goal configuration without colliding with any obstacle. So a collision-free path that is optimal under some cost function, and we will start here with the shortest path. So there should be no other path around that visits a sequence of states from the valid states and should reach the goal more quicker or faster or on a shorter trajectory. That's something that shouldn't be there. There may be other alternative paths which are equally good, but no better paths. And then we found an optimal solution. Our algorithm computed an optimal solution to that planning problem. Next thing I would like to look into is the configuration space and try to at least very briefly introduce the concept of configuration space. So the planning problem actually lives in kind of our real world. And we have typically a robot, let's say a physical object that moves through the environment and can control its own configuration in order to go from A to B. So we are living in the real world, but internally we are using something which is called the configuration space, and perform the planning in that configuration space. So the configuration are kind of the configurations the system can be in. So for example, if you have a robot which also has an orientation, this orientation would be taken into account in this configuration space. But it's not just that, it basically, the configuration in configuration space or state in configuration space allows you to describe where all points, the full shape of the robot actually live in the world. So if you, for example, have a robot with a joint, then you have a joint angle that you may be able to control, which changes the configuration of the robot and thus the points that are occupied in the real world. So you need this concept of configuration in order to decide if a certain configuration is actually collision-free. So if you have, let's say, an arm, and whatever the shoulder is, defines the position of that arm, then just based on this shoulder position, you can't decide if this is collision-free or not. So my arm may be collision-free, and even if I don't change the configuration of my shoulder, that will lead to a collision. So you need to take the full configuration of the arm into account and take also the joint angle here into account and the representation of the platform itself in order to make the decision if we here are in an obstacle-free or an obstacle configuration. And so therefore we have in the end states in configuration space. And based on this state in configuration space, or a configuration, in short, that allows us to decide if it is collision-free or not. Quite often those configuration spaces are discretized. So for example, let's say an object can move whatever just on a 1 centimeter grid and has a 1 degree discretization in its orientation, just as an example. So I can show here a very simplified discretized configuration space. So this is basically an occupancy grid map where you have cells, very large cells now. And so we assume that the robot can only be in the center of every grid cell and can basically move to its neighboring cells. So that's a very simplified form of a discretized configuration space. And this, in this case, is just a 2D configuration space, assuming the robot can move arbitrarily in all directions, for example, as an omnidrive, and then just can move from grid cell to grid cell. Again, this is an approximation. We discretize the space. And if we are generally living in a continuous world and we discretize it, it is an approximation. But this is one example for a discretized configuration space. And then the planning system only uses this discretized configuration space, for example, in order to plan a path from the start location over here to a goal location over there. Which states does a system need to visit in order to come up with a valid trajectory that guides the robot along that path? So this is an example for such a discretization. In general, we split up the configuration space in free space and in obstacle regions or in occupied space. So then we have a workspace, which is a set of configurations and we want to live in that part of the space that is collision-free, so where the system can actually be. So our workspace is basically a general space of real numbers, for example. This is, for example, our workspace over here, and it contains a set of obstacles, which are shown here in this greenish-gray color over here. So this is basically the surrounding, let's say, kind of the wall, so to say, and you have some obstacles sitting here in between. And then we have configurations that describe the robot. This is, for example, an initial configuration and a goal configuration. And with those configurations, we can actually describe the shape of the robot. And this is done with this function A of Q. So Q describes the configuration, again with my arm, it could be the joint angle and the position of my shoulder. And then this function A of Q basically maps the robot into our space. So which parts are occupied here in that workspace. So that we can make the decision, will this lead to collision with an obstacle, yes or no? So what we're doing technically is we are taking, we define the free space as the configurations in configuration space. So my configurations in configuration space, so that the A of Q, so the shape of the robot, intersected with all obstacles gives me the empty set. So these are basically all the wide regions over here, so where there is no overlap with of the robot with an obstacle. And then the occupied space is simply the whole space minus the free space. And this is one way how we can describe the free configuration space, so the configurations that the system can be in without colliding with obstacles that we have in that surrounding. And then what we typically do or we need to have two configurations in this free space, an initial configuration or our current configuration and our goal configuration. So then the goal is to find a path that can connect in configuration space, the initial space and the goal state. So it could, for example, look like this. This could be a trajectory here in that configuration space, and that can be described by a function tau from 0 to 1 that maps only into the free space. So it's not allowed to map into the occupied space, because that would then lead to a trajectory which leads to collision. So that tau of 0 is my initial configuration and tau of 1 is the goal configuration over here. So I'm basically having a function which describes which states I need to visit in order to move from the initial configuration to my goal configuration. And that means we can actually do the planning, so find that function, that mapping over here in our configuration space, so that we basically have a point that we move through the C space, which describes the trajectory from the initial configuration to the target configuration. And this is kind of a more formal definition how I can perform this, or how a trajectory, a path or a solution to the planning problem looks like in this configuration space. So this configuration space or C space is not necessarily continuous, it is shown over here. Often it is actually discretized. And there are different ways how I can discretize my configuration space. So the configuration space can be discretized in different manners, and there are kind of two general approaches how I can do this. The first one is a combinatorial approach. And this is something that we will be using here in the lecture, which basically says I take all possible states and I break them, discretize them down into smaller states, like a voxel representation in the 3 space or a grid cell representation in the 2D space. So similar to an occupancy grid map, for example, if you just consider a set of 2D states. So this is what is called combinatorial combinatorial discretization, which then leads to a combinatorial planning problem. The problem in here is that the dimensionality of the configuration space actually increases. So there's a robot which has a lot of different joints, for example. This space gets very high dimensional, and the number of discretized states that I'm actually generating is exponential in the dimensionality of my search problem. And this can be a problem. So that's something that you would apply if you're planning in low-dimensional spaces, 2D spaces, maybe 3D spaces. Then you can do this discretization or this combinatorial discretization. If you go to 10, 20, 30-dimensional spaces, this is not going to fly anymore. What you then do is use sampling-based techniques. That means we don't necessarily discretize our state space uniformly, but we sample possible configurations. And we are sampling possible configurations in C free, so we need to have a technique to generate configuration in this C free space which are close to a given configuration, for example, close to our current configuration. So that we then, by sampling, we are basically expanding the states around our current configuration and expand states, sample states, and then plan only in those sample states. And we are expanding or sampling these states during the planning process with the hope that with an intelligent strategy, we only need to sample a small subset of the overall space, and then through the sampling process don't need to discretize all the different dimensions. We only need to explore the states which kind of look as if they would be promising to lead the robot to the goal. And if this is the case, if we have this additional information at hand, then these sampling-based planning techniques can be very efficient. So with those two different approaches, we can actually generate our C-space discretization. So that the next thing we need to do, we need to search through these possible configurations in order to find a sequence of states in configuration space that guides me from my current configuration to my goal configuration. I said already, we need to search. So planning can be solved by using search algorithms in order to search the configuration space for a sequence of configurations that guide me from the current configuration to my goal configuration. And we have, again, two different concepts in search strategies that we want to distinguish here. These are the uninformed search techniques and the informed search techniques. So again, the goal is to find a sequence of actions, so a path, that guides me from my initial configuration to my desired goal configuration. And how do I find this sequence? I can search through all the possible states that I'm expanding in my configuration space, and then start from my initial configuration and hope to at some point in time end up at my goal configuration. And if I found that the transition from the initial configuration to the goal configuration, I also found a sequence of actions that I can actually execute in order to come from my current state to my goal state. And the uninformed search algorithms are kind of the simplest form of search algorithms, and they're kind of form of a blind search. They are blindly searching through my configuration space. They may need to take into account how many steps they already have been taken from the start location until they reach a certain state, and then they always try to make the decision of expanding the cheapest node, for example, in order to explore the space further until they find the goal configuration. But there are different ways how these costs can be taken into account. It can be a search tree that I'm expanding. I'm just looking into the level or the depth of that search tree. I may have a cost function associated with every state, so individual cost functions for individual transitions between states that may be taken into account. These are different variants of this uninformed search techniques. But what the uninformed search technique is not doing, it doesn't exploit any additional information about the problem or additional knowledge about the goal or things, let's say, upper bounds or lower bounds, for example, that I can generate in order to say something how cheap or how expensive a trajectory may be if I know where I am with respect to a goal configuration. So the uninformed search technique don't use this. They only use their cost function. They're expanding their own cost function. And popular algorithms in this context are breadth first search, depth first search, uniform cost search. These are commonly used techniques which we'll introduce with one slide basically each in order to kind of guide you towards from the uninformed search techniques towards the informed search techniques, because A* is an informed search technique. In contrast to the uninformed search techniques, the informed search techniques use additional information about the environment and my goal configuration. And that's something what we call a heuristic. A heuristic is an estimate of the cost. So how expensive is it in order to, if I start in my current configuration and I want to reach a goal configuration, to reach that goal configuration from my start configuration. Of course, if I would have the perfect knowledge about this, my planning problem would be very easy because I could just make a gradient descent in this cost function. But what the heuristic does, it provides an estimate for that. So it can estimate the cost. These are not the actual cost, but they're an estimate of that cost. And how can I exploit an estimate and still come up with a good solution, or maybe even an optimal solution? And that's what the informed search techniques are about. They are using this heuristic to speed up the search, so to find the goal configuration more quickly, but the quality of the found solution should actually be still the optimal solution. Not all of the informed search techniques are optimal. The first technique we'll discuss, for example, greedy search, is not an optimal optimal search technique that leads to an optimal trajectory, but A star, for example, is. And for that, we need to have certain constraints on how that heuristic could look like or should look like. But what you can in general say that these informed search techniques use a heuristic, use additional information in order to find a solution faster. So if we have an optimal search algorithm, that means an algorithm which provides me with a trajectory which is optimal, that means there's no better trajectory or no better sequence of actions guiding the robot from its current location to the target location. The question is under which, how do I compare algorithms, under which criteria or things I'm actually evaluating and can compare different search algorithms. And there are a couple of things I can take into account. The four kind of most commonly used criteria for evaluating search algorithm are shown here. So it's completeness, optimality, time complexity, and space complexity. So what does that mean? Completeness means, does the algorithm actually find a solution, a valid sequence of configurations from the start to the goal location in case it exists? So of course I can define a planning problem where there is no path from a start configuration to a goal configuration. So for example, if I have two rooms, but there's no door between the rooms, and the robot is in room number 1 and the goal's in room number 2, there's no way to reach the goal configuration, and that means you can't find a path. But the question is, if there is a doorway, can I actually guarantee that the algorithm will find it? And this is what I refer to as completeness. So does the algorithm find a solution if there exists one? And of course, we would like to have complete algorithms because we don't want the algorithm to abort and say, can't find a solution, although there is a solution. That's something that we would like to avoid. So the algorithm should report a solution if there is one. The second thing is optimality. And this is what I already referred to before. Is the result, the path that the planning algorithm actually generates, is this the optimal one or is there a better one? Optimal under some cost function. So there can be other alternative paths which are as good as the one that I have, or they are worth, but they can't be better. If this is the case, then I found an optimal path because there is no better path under the specified cost function. If people talk about optimal planning algorithms, you always need to remind yourself that this is under the defined cost function. That doesn't mean this is the best algorithm for any robot navigation problem. It's just kind of the algorithm which generates the best possible solution under the assumptions that have been made. And those assumptions are the cost functions, the discretization of the state of the configuration space, and other things, just to keep that in mind. So be careful with the word optimal algorithm or optimal technique unless you specified what optimality means for you. And then there are things like time complexity and space complexity. So how long does it take to find a solution? How much memory is needed to do that? And in this kind of how much, we typically don't refer to whatever, 20 seconds or 10 gigabytes. We refer to that in relation to the number of states or the number of transitions which are out there. So it's a complexity, for example, provided in terms of the big O notation. So it's not just kind of whatever, it takes 10 seconds to complete a path. It's more like it's an algorithm which has whatever, is linear in the number of states and quadratic in the number of transitions, for example, or edges that we have in this search problem. So these are things that I want to take into account. So in the end, I want to have algorithms which are complete, which are optimal, have a low time, the low space complexity. That's kind of the best thing I want to have. Okay, so now let's dive into some examples of uninformed and then informed search techniques. And we can actually gradually build them up and then kind of combine all the different search techniques that we're now presenting so that in the end we come up with the A-star algorithm. We start here with the very basic search algorithms, breadth first search, BFS, or depth first search, DFS, where you are expanding your configuration space in a certain order, not taking any cost into account. So you're basically expanding a node, and you can basically say every node that you're actually expanding has a certain cost or has a fixed cost, a cost of 1 associated to this, and you may want to find the kind of number of states that you need to visit, which is the smallest number of states to reach your goal location. So this is kind of a tree where you're starting. So 1 is your initial configuration, and you're expanding basically the neighboring states that you can reach from the state number 1, and you stop once you found your goal configuration. So for example, from 1, you have the neighbors 2, 3, and 4 that you may consider to visit, and 2 has the neighbors 5 and 6, and the state 5 has the neighbors 9 and 10, and so on and so forth. And you're basically searching through this tree that you're expanding, your search tree, until you find your goal configuration. So you start over here, and in breadth first search, you're basically passing this level by level. So you start with your initial configuration, and then you first inspect all the neighbors, so 2, 3, and 4. And then you inspect the next level, then the neighbors of 2, which are 5 and 6, neighbors of 3, 3 has no neighbors, nothing to do here. Neighbors of 4 is 7 and 8. And so then you have kind of 5, 6, 7, 8 is the next level where you haven't checked for the neighbors. So you start checking the neighbors. So from 5, it's 9 and 10, and so on and so forth, until you find, in this example, for example, state number 12 as your goal configuration. So this is breadth first search, and you're expanding this basically row by row. And you can see this is basically a cost of 0 because it's the state that I'm in. 2, 3, and 4 are states which I could visit with a cost of 1, so making 1 movement, so to say, from one state to its neighboring state. And then the second level would require 2 movement steps, 3 movement steps, and so on and so forth. So by searching through this space, I actually have an optimal algorithm, assuming that they all have kind of a cost of the same cost in which I'm expanding that. And it's also a complete algorithm. It will simply go through all states and will find the solution if a solution exists. Somewhat different is depth first search. Here I'm basically not going level by level. I'm basically checking for the first neighbor, and then its first neighbor, and then its first neighbor until there are no neighbors. And then I'm basically backtracing back and expanding all the other states. So I'm basically going deep in my search tree. This has somewhat different properties. It's definitely not an optimal solution because I may find a path by just going into the depths to a goal configuration, although there may be a shorter path just by going through a different neighbor. And given that I'm exploring going deep first and not expanding it level by level as for a breadth first search, then I may not come up with the optimal solution. It is a complete algorithm if we are in finite spaces, so if there's just a limited number of states I can explore. If this is an infinite number of spaces, I may run into a kind of an endless loop or an infinitely large corridor down here, although there's a very short path over here to my goal location. And I may miss this and therefore will not find a solution, even though a solution exists, which is maybe even a very simple path. So if neighbor number 8 would be actually the goal, but I'm starting with 2 and continue forever searching this part of the tree, I may not find the configuration, although it would actually be pretty close. So there's not an optimal solution, and it's not complete in infinite spaces. It has different complexities. They basically depend on the branching factors. So how many neighbors do we have? How deep is the goal? So in which level is the goal? So basically how far the goal is away, or the maximum depth of the tree. These are different parameters on which those two algorithms actually depend on. And breadth first search is kind of the absolute basic technique that we may want to use for path planning problems. Often, however, we don't have equal cost for all those expansions. So some trajectories are more expensive and some trajectories or some transitions are cheaper. And this leads us then to a so-called cost-sensitive search, which is still an uninformed search because it only uses this cost function and it doesn't take any further information into account about the goal. And what we have here is that all nodes are treated uniformly, so in the same way, so independent of the level, for example, they are in compared to BFS and DFS, but they are distinguished based on a cost function. So there's a cost function which tells you the transition, how to go from one node to another node, but the nodes itself are treated uniformly. Therefore, it's called uniform cost search. It doesn't mean we have uniform cost. So this may be a bit confusing. It doesn't mean we have uniform cost in that search. It means all the nodes are uniform, but we have a cost or different cost from the transition to go from one node to the other node. Okay? So, and what this algorithm does, it takes into account the accumulated cost on the way. So if we have my graph over here, and I have here numbers on those edges, and these are costs of going from a node 1 to a node 2 would be a cost of 2. To go from 1 to 6 would be cost of 7. So this is what those numbers mean here, written to the edges. And what the algorithm does, it looks into the accumulated cost. So the cost that I have invested so far, so my path cost so far. So if I'm, for example, the cost of this node number 5, if I start at 1, would be 2 plus 4 equals 6. So this would have an accumulated cost of 6. And this node over here would have an accumulated cost of 5 plus 6 equals 11. So this is a so-called G cost, or the accumulated path cost. And what the uniform cost search does, it basically always expands the node which has the smallest accumulated path cost. So we are basically always looking, what is the nodes which I reached in the cheapest possible way so far, and I'm trying to expand those nodes. And this leads to a behavior which is actually similar to a breadth-first search if we have uniform costs, so if all those costs would be 1. But often this is not the case. We have different costs for different transitions, and then the cost-sensitive search is actually the algorithm that you should use because it expands the cheaper nodes further, or the nodes which lead to a cheaper accumulated path cost. And it's an optimal and complete algorithm. So you will find the optimal solution, and if a solution exists, you will actually find it. And this is kind of a standard approach in the uninformed search technique, that you're just saying, okay, let's see what I pay in the end, how expensive it is to reach a node, and I'm always kind of expanding the cheapest node until I find my goal location, because if I do this strategy and find the goal, I can actually guarantee that I found the cheapest solution, because there's no other cheaper path out there, any other node I can reach with a lower cost, and I haven't found the goal so far. So the first time I find the goal, I know it is actually an optimal solution. And again, if I use this uniform cost search, but I have uniform costs, so if all the costs are 1, which is illustrated over here, this basically means we are passing through it level by level, and then the uniform cost search basically degenerates to BFS. So there's a direct relation between uniform cost search and BFS. So BFS is a special case of this uniform cost search with transition cost of 1. So there's a direct link between those techniques. There's also another link. So you may have experienced the Dijkstra's algorithm, which is an algorithm which expands the whole search space and tries or compute the shortest path from all nodes to one node. For example, if you start your expansion from your goal node, and if you run this search, starting basically from your goal configuration and expanding the whole tree, and save those G cost for all the nodes that you expanded, so the whole configuration, then this is actually Dijkstra's algorithm. We get the same result as Dijkstra's algorithm would do. So there's a direct link between the uniform cost search and Dijkstra's algorithm, which may allow you to relate that to techniques you potentially have seen so far. So this is a part of the uninformed search techniques. So uninformed again means we're not exploiting any further information about the goal or about the problem that we are using. And with this we can define rather simple search strategies, and these strategies will lead to optimal solutions, and some of them are also complete. That's kind of great. The problem with those techniques is it takes a while until I actually find my goal configuration. So the question is, can I do better? And can I generate solutions which can exploit somewhat more information and through that additional information can find the goal configuration quicker. And that's what the informed search techniques are about. So the informed search techniques are, in contrast to the uninformed search techniques, they don't use any. They use further information about the problem in order to be better than the uninformed search techniques. So we use additional knowledge, and this additional knowledge is encoded in a so-called heuristic. A heuristic is a cost estimate. So it's a function that estimates the cost from a configuration, from any input configuration to the goal configuration. And this cost will not be the actual cost, but it's a hint. It gives you some idea how that cost could look like. And of course, the better that estimate is, the better, or the faster I can probably find the goal configuration. If your heuristic is completely random, of course, it is not of any help, may even distract you and guide you into the wrong direction. But often we can actually provide you with certain bounds on cost, like whatever, reaching the target configuration from my current configuration. You can't do that better than a certain distance, because you take the straight line distance between two configurations into account. You can say there can't be any faster or shorter path rather than the straight line distance, assuming that we're living in an Euclidean world. And so this allows you to provide a bound for that cost. And this is very, very valuable, which you can exploit in the search and to guide the search, expanding nodes which potentially lead to the target location or to the goal location faster than the expansion of other nodes. And that's exactly what the informed search techniques do. They look into nodes which are promising, which are most likely to lead to a goal configuration quicker. So they are there, these heuristics, to speed up the search. And one technique is greedy search. In greedy search, or the simplest form of greedy search, we are basically we're only taking into account this cost estimate. So how good can I actually reach from that node my goal location? So that's kind of the simplest form of greedy search. There are more advanced ones. And you're basically just checking, using your estimation function, your heuristic, how far is it from that state to the goal? And you're always looking into that state which promises you to be the one closest to the goal under this heuristic. So consider you have expanded a certain number of states and you're kind of here in that state number 4, and assuming our goal would be that state number 12, where we don't know how to reach it yet. Then what the heuristic function can do, it tells you, okay, from 4 to 12, you have the h function tells you an estimate of the cost. Although you haven't expanded those nodes yet. So you don't know how they look like, otherwise you would know the cost already. So you haven't expanded them, but this h function can give you a good guess on what that cost could be. And then, if you're having current nodes to expand to look further, you would always take the node which promises you the shortest distance to the goal under this heuristic. So the greedy search ignores the accumulated path cost so far. So it ignores how expensive it was to reach for. It just says, from all the nodes that I've seen, always expand the one which guides me closest to the goal. So it greedily optimizes based on that heuristic. And this leads to algorithms which typically find the solution very quickly. So they are faster in finding the goal location if we have a good heuristic. The problem with this algorithm is it's not guaranteed to find actually the optimal solution because your heuristic is most likely not be the optimal solution and you will not, and given that it's not optimal, you cannot guarantee that you will actually find the optimal solution. So you get your result quicker, but the quality may suffer. And what we can then do is we can say, okay, let's combine uniform cost search and the ideas of greedy search to come up with a new algorithm, which on the one hand side takes into account the accumulated path cost so far, but also takes into account the estimated cost to the goal. And this is what the A-star algorithm does. So A-star, you can see A-star as a combination between uniform cost search and greedy search. So uniform cost search in the sense that it considers the accumulated path cost, and greedy search in the sense that it takes the heuristic into account and actually computes a sum of accumulated cost plus a heuristic of how expensive it is to reach the goal from the current configuration that I'm considering. So again, in my example, if we are again in our node 4, what A-star would do, it would take a sum of two costs into account. The cost of reaching 4 so far, so the cost that I know, the actual cost that I computed, my accumulated path cost, G, plus a heuristic, how expensive it is potentially to reach my goal location, so my state 12 in this example. So through this combination of G and H, A star can provide you with an algorithm that combines the advantages of both algorithms. You need to have some constraints on the heuristic, so you can't take any heuristic, but if you choose a heuristic in a smart manner, then you actually end up with an optimal and also complete algorithm, which is called A star. And A star is an algorithm that actually has been developed in the robotics community. So in the late 60s, Niels Nielsen at the Stanford Research Institute was involved in the project was called Shaky the Robot. So one of the, this robot over here, which was one of the very early robots that could do solve navigation tasks and perception tasks that are, let's call it, similar to the tasks that robots can do today, of course in a simplified setup under more constraints, but it's very impressive to see what Shaky the robot was able to do in the late 60s, given the capabilities that they had at hand at that point in time. And a lot of relevant algorithms that are out there today and are standard algorithms in robotics or in AI today have been developed at SRI at that time. And among them, also the A star algorithm, which is today really the gold standard algorithm in AI for informed search and used in the majority of planning systems out there, is A star or some variant of the A star algorithm. So it's one of the things where the robotics community actually came up with new solutions that impacted also other fields. So how is A star used for that type of problem? So we're using the A star, this algorithm, which combines the accumulated path cost so far and the estimate of the cost for reaching the target location in order to plan a path for the robot from a start location into a goal location. And what we typically assume in here is kind of known poses and a map of the environment. So we assume to know how the environment looks like. We have a geometric representation of the environment most of the time. Often that's an occupancy grid map or a grid map structure, but it could also be another discretization, polygons of the environment, for example. And we assume always to know where the robot is in the environment. So we assume to have a working localization system in hand. And then what the algorithm does, it provides you with a sequence of configurations that the robot needs to follow in order to be guided from its current location to the goal location. And if the robot drives along that path, it will be the optimal path. And it uses a heuristic to do that. And the heuristic depends on your cost function, because this heuristic always needs to underestimate the actual cost. So you're not allowed to overestimate the actual cost. If you're overestimating the actual cost, you don't have the optimality anymore, the property of optimality. But if you're underestimating the cost, or smaller or equal, then you actually have a heuristic which leads to an optimal solution. And if we are looking into the shortest path problem, not the fastest, but the shortest path problem, the straight line distance is a very good tool to use. Assuming we are living in a Euclidean world, which we do most of the time, depending on the planning problem you want to solve, but if we are moving to the 2D world, for example, we can very well describe it by Euclidean space. Then the straight line distance between, let's say, two xy locations or two xyz locations is the shortest connection between those two nodes. So it's a lower bound for the length of a path going between those two configurations. And this lower bound is exactly what I need for my heuristic. So the straight line distance is a very good heuristic for planning in the 2D or 3D world. Of course, you may need to take orientations into account, which are non-Euclidean, or if you look to, for example, shortest time planning algorithms, so we want to generate the fastest trajectory, but then you can still use the straight line distance by saying the fastest possible way from this configuration to another configuration is driving with the maximum speed that the vehicle can actually drive along a straight line distance. You can't be faster. So you can still use these ideas of a straight line distance in order to come up with an admissible heuristic, so an underestimating heuristic for this A star planning problem. And so that's what kind of a coarse description how A star can be used for robotic path planning. So let's see how that looks like in our discretized configuration space that I have actually seen before. So what we see over here, we have this discretization of the environment. Our system starts over here and wants to go down here. And what it does, it basically will expand those nodes over here and will always expand the nodes based on a combination of the actual path cost accumulated so far to reach a node and the predicted cost from that state to the goal. So what I can do is just kind of run this animation once, and then we can see how that evolves. So you see always the nodes which are expanding. So for those gray states here, we actually know the cost. The other costs here are actually boundary cost, or states where not all the neighbors have been explored yet, where I know the cost already, and I'm basically expanding that, always expanding these new nodes, which are here the kind of the boundaries between the already explored space and the unexplored space, until I find my goal location, and then this gives me the optimal path from my start to my goal. So just kind of rerun that video. So with these explanations, you may be able to kind of better appreciate that again. So you see how the nodes are expanded, and the yellow node is always the currently expanded node, and you can see the search is actually guided towards this state. So you're always expanding nodes, and it prefers to go down here because it's more promising to reach a goal location until it reaches the goal. And nodes up here, for example, are not explored because the heuristic tells me it's probably not a good idea to go here because you're moving further away from the goal. So this is unlikely to be a good path, and it avoids exploring those nodes. And you're still not sure if this is the shortest path because you do not know if there's a doorway, for example, over here, or if this is the shortest path. So the algorithm basically expands these two possibilities until it finds the optimal solution to the goal. And that's kind of how A star works. So let's dive a little bit deeper into the A star algorithm. What A star does, it minimizes the cost, which is a combination of the actual accumulated path cost for a node. So how expensive it is to reach a node n from an initial state. So from the initial state to n, how expensive is it? So this is the G cost that we used in uniform cost search, the accumulated path cost to reach a node. And then it also takes a heuristic into account, h of n, and h of n is an estimate starting from n, how expensive is it probably, or what do I estimate how expensive it is to reach my goal location. So from n to the goal. So G is from start to n, and h is from n to the goal, where G is the actual cost and h is just an estimate. And then what A star uses the so-called F cost, and the F cost is the sum of the G cost and the H cost. So the sum of what I know already plus my estimate. So I'm basically always using a combination of something I already know and I'm estimating the rest. And this is what this F cost is, a sum of the cost I already know and my heuristic cost. So it's a combination of the cheapest solution so far and an estimate to the goal. And where this overall sum is the smallest sum, this is the node A star is expanding. So A star will always expand the node which the smallest F cost among the nodes it has already considered, or it is currently considering. So it basically expands this search tree and always expands the node which has the smallest F cost. But the question is, how must H look like, the heuristic look like, so that we actually find a good solution? Because it's clear if H is completely arbitrary, this is not of help. We actually mess up our cost function. So there are some properties that H must have in order to come up with the right solution. So the first thing is, of course, if I'm at the goal, but that should be pretty clear. If n is the goal state, then h of n should be 0, because if I'm at the goal state, I'm at the goal state. There is no further cost, but that's kind of easy to achieve. What's harder to achieve is that the cost for all nodes must be, the estimated cost must be smaller than the actual cost. So I always must underestimate the actual cost. I'm not allowed to overestimate the cost. So if that means if there's a path from n to the goal, and I say, my heuristic says, oh, this cost is whatever, 10 units, but the actual cost is 8 units. That's something which is forbidden. I'm not allowed to make an estimate that is more expensive than the actual cost. I always need to make sure that my costs are smaller than the actual cost. So I need to underestimate my cost. So if H star is kind of the actual cost, the thing which I don't know, but which assume we would know it. Assume we would know the perfect cost to the goal. Then they can call that function H star of n. Then H of n must always be smaller or equal than H star of n. Of course, we want to push it up to be as close as possible to H star of n, because of H star of m, I know all the cost, and then my planning problem is super easy because I just need to do a gradient descent in this cost function. but this is typically not the case. I can't know the optimal accumulated cost for all nodes on the way already. So I want to be as close as possible to H star, but it must always be smaller. And if this is the case, I have a so-called admissible heuristic. And if I have an admissible heuristic, A star will lead to an optimal solution. And again, a standard admissible heuristic for planning in Euclidean spaces is the straight line distance. So that's a very good starting point, which already is a quite good heuristic. Again, if you know more about your problem, you may take additional information into account. But if you just know I'm in a Euclidean space, you don't know anything else, straight line distance is a very good choice. So what happens, just as a side note, if H is actually larger than H star? So if it's not an admissible heuristic anymore. In this case, you lose the property of optimality. So the result that you get is not guaranteed to be the optimal solution anymore. But you can say a relationship by how much you overestimate, you can make another bound on your solution. So if you have, let's say, a heuristic which is up to twice as expensive as the optimal heuristic, so you're overestimating cost, but not more than a factor of 2, then you can show that the result that you get is only up to a factor of 2 worse than the optimal solution. And this is a property that some of the anytime algorithms, like anytime real-time A star, RR star, is actually exploiting in order to start with the path which may not be the optimal one, but which is very, very efficient to compute, and then kind of optimize it the more computational resources you have available. So as a rule of thumb, you must be smaller than H star to be optimal, but the larger Hn is, the faster your search gets. So you want to make H of n as large as possible to be fast, but still smaller than H star in order to find an optimal solution. And depending if you want to give up optimality and optimize for speed, or you say speed is important but not that important, I still want the optimal solution, you can try to overestimate or underestimate H star. So it basically depends on the solution on your application, if it is okay to have a path cost which is slightly more expensive than the optimal cost. But if you find it therefore in just a fraction of the time, you may use your computational resources in a smarter way for your problem. So it may be worth to actually make that trade-off. So how does A star work as an algorithm? We said we are always kind of we are basically expanding the search tree and always expand the tree, the nodes which has the smallest H cost. In practice, it's like that, but it's slightly more complicated. And if you want to implement this, what you need for that, you need to have a priority queue. So a queue where you can put in nodes, and the queue orders the nodes, and you can always get out the cheapest possible node. And what can also happen, given that we in the end have a graph structure of our configuration space, so we can reach a node through different ways, we need to be able to update nodes if we find kind of a cheaper way for reaching it. And this is something that we need to take into account. I don't want to go now through an algorithmic description of A star. I just want to go to basically a flowchart describing the different stages of A star. And this is a drawing from Joseph's book. So, and we can just go through those individual steps of the A star algorithm kind of as a pseudocode or flowchart-based description on how A star works. So we start somewhere over here, and what we have an open set O, which are the nodes that I'm currently considering. This is my, my priority queue, and I have a list or a storage container C, which are the closed nodes, so those nodes which I have already investigated. I know their cost already. I'm not need to take them into account anymore. Okay, so I start and say, is my open list empty? Is there any nodes that I haven't fully investigated? I haven't visited all the neighbors and know the cost now finally. If this is the case, then I'm actually done, because then there's nothing to be done anymore. That means basically I explored my whole state space. You typically start with O being the initial configuration of the robot being inserted to that O list. So I'm not starting with an empty list. So that's basically the initial configuration. Okay, so that means we're not done yet. So what do we need to do? So we need to pick n best from O in the way that it has the smallest f cost. That means I'm picking out from my open list the node with the smallest f cost. So the smallest accumulated path cost plus heuristic estimate. And this is the next node I'm going to expand. And this is in my search tree, the cheapest node in kind of the boundary of nodes to explore, and I'm actually picking that one. Okay, so what I do, I remove it from my open list, so from the nodes to inspect, because I'm expecting it right now, and then adding to my closed list, so those which are already done. I don't need to investigate them further. Then I check if this node that I just took out from my priority queue, is it actually the goal configuration? If it is the goal configuration, I'm happy, I'm done, I found the goal configuration, everything is good. But in the majority of cases, this will not be the case because I need to expand a large number of nodes until I find my goal. So assume we are now on this node track over here. Then what I need to do is that I need to look into all the nodes which are neighbors of that node that I'm inspecting. So I'm taking that node and basically now saying, okay, it's not the goal node, so I need to look further. Let's check all its neighbors. So I'm basically expanding all those neighbors and see and want to check for those neighbors which are not in the closed list, so those which I haven't visited so far. It could be that I visited them already because I was next to them on another path through the environment, because we're in a full graph, so there may be several routes to a configuration. And then if I'm taking this neighbor out and it's not in the closed list, I need to check, is it already in the open list? So is it already in my nodes I actually need to inspect further? If this is the case, so if it's not the case, if it's not in O, I actually need to add it to O. So it's a node I actually need to consider. So next thing to visit. If it is not the case, that means it is already in O, I need to see if there's actually the new path that I found is actually a cheaper way for reaching it. So if it is only if it would have been in C, so all the nodes that I'm in C are already done. The cost can't change anymore. Everything which is still in O may change because I may find a cheaper path to reach that node. And this happens over here. I need to make the check if the cost through the nodes that I'm expanding is actually cheaper than what I was knowing about it before. So in this case, I need to update the cost and basically need to update the cost in O. And then I'm done, and I'm again checking if there's anything else in O. Potentially, I'm now expanding the node that I've just added, or one of the neighbors I just added, because if the cost from the previous node to one of those neighbors was small, it's likely to be now the cheapest one. So basically, I'm expanding towards the goal. But it could also be any other node which is cheaper. This is what the priority queue does, which is realized with O. It always picks out the cheapest node out of the open list, and so this is the node that I'm expanding. And this is basically the algorithm, which can be implemented with a couple of lines of code, so 1 to 2 pages of code you need in order to get that done, assuming you have a priority queue for your implementation, which does the handling automatically for you, and that's the way how you would then implement that approach. And this gives you an optimal algorithm, which is complete and which is comparably fast. The only thing you need to do is you need to specify your path cost, and you need to specify a heuristic, which is admissible. That means that underestimates the actual accumulated path costs. And with this, you have your A-star algorithm being implemented. Let's see now how that looks like if we apply that to robot navigation. We could apply it out of the box and just plan path, but this is often not the best thing we can do. We have to make a few small tweaks in order to do better. We first will do this for simple 2D playing problems, but then also see how we can actually exploit that in order to combine this high-level planning that we discussed and this bit more low-level planning, this collision avoidance, in one go. So, application to 2D path planning, that's what we start with. So if the robot is in a certain state in this configuration, we typically use the N8 neighborhood. That means on a grid map, we can go into all neighboring states. So again, very often we do this on an occupancy grid map and plan a path on an occupancy grid map, at least in low dimensional spaces. If we have very complicated configuration spaces, that's not what we do anymore, but often we plan in a 2D space, and so the robot can basically rotate on the spot and then move into different neighboring configurations. So that if I'm starting over here, and I want to go down here in this room, you can see here the expanded nodes. It's kind of this gray area. The darker the gray, the more expensive the cost. And we are expanding those nodes until I actually find the way to the target location. That's basically what we have described so far, how the planning actually works. And in its basic form, nothing needs to be added to that. You can plan your path for your robot, the sequence of 2D grid stalls you need to visit in order to find an optimal solution to the path. That's something that works. However, there are a couple of assumptions which we have made on the way, which may not hold for real-world robotics. And we need to always make sure we revisit our assumptions to see, are those assumptions actually valid and justified. So the first assumption we made is that the robot knows its own location. The robot always knows where it is. That's kind of an assumption which we often say, maybe we can assume that. But the question is, what the quality of my localization estimate? How accurate is my localization actually? Is it accurate up to 20 centimeters? We can say, okay, that's kind of something I can typically assume when navigating with a typical sensor setup in an indoor environment. But that may be different if you go really, really close to obstacles, let's say just 1 centimeter next to an obstacle in order to optimize your trajectory. In this case, your pose estimate, which has 20 centimeters accuracy, may not be good enough anymore. So you need to be aware what means you know your own location. So if you need to be really precise, millimeter precise, that's something which most systems are unlikely to provide to you, at least can't guarantee it. What you then assume is that your map is correct. So assume the map of the environment is correct. So either your pre-given map is correct or you use your sensor data to update the map, but you assume at the point in time when you start the planning process, you know that your map is correct. And that's something which is, again, an assumption. If you have people which walk through the environment, that may not be actually the case. And so we need to find a way in order to deal with this problem. And the other question is your motion execution actually being correct? If you say go a meter forward, does the system go a meter forward, or does it maybe even drive a little bit to the left-hand side? Just say 1 degree to the left, because there's a small drift. If you need to take that into account in the planning process, it gets much more complicated. A-star ignores this. And so it means basically that you shouldn't drive really, really, really close to walls. If you do that, really, really driving close to walls and just turn 1 degree more to the left-hand side than you actually should, you would actually collide into the wall. So although A-star computed a collision-free path, who guarantee that it is actually collision-free in the real world? No one. And so you need to revisit always your assumptions. What are the assumptions that you made? And maybe you should change your problem a little bit to at least not completely avoid the problem that we have, but being more robust under small variations of those problems. So if I say, most of the time actually well localized, but sometimes maybe not perfectly, can I take that into account in the planning process, not necessarily in the planning process itself, but in the way I formulate the problem, that the solution that the planner generates is actually less sensitive of, for example, leading to a collision if those assumptions are at least slightly violated. So potential problem that I have is that the robot is slightly delocalized, that one I just said before, so your pose estimate is slightly wrong. The other thing that you can see if you watched a few of the A-star algorithms finding a path from the current configuration to go location, that the path often guides very close to an obstacle, because you want to drive as fast as possible and you don't want to make a small detour. It's totally fine to go just a millimeter next to a wall because it's collision free, right? So according to the planner, no overlap between the robot and the wall, even if you just pass by with a millimeter of safety distance. The algorithm would say, yeah, perfect, it's collision free. If you could guarantee to execute that millimeter precise path, that would be the case, but that's something we can't do in reality. So you may want to increase your safety distance to obstacles a little bit. Don't make the trajectory substantially longer, but try to avoid to go to really close to obstacles. That's one way how we can actually deal with this potential problem. Something else that we can see if we have a grid map, we basically have discretizations in 45 degrees in the orientation of the platform. And so if the typical routes that you take or the corridors in your environment, for example, are not in line with the grid structure, that can actually lead to suboptimal trajectories just because of the discretization of your state space. You may get actually weird navigation trajectories that the robot does some weird movements when navigating through the environment because you did a too-coarse discretization of your configuration space. And that is something you may also want to take into account. So we now want to look in the remaining part of the course on how can we actually deal with those two potential problems and see how we can actually tackle that. So what to do in order to avoid that the robot is often guided really, really close to obstacles, because if it is slightly delocalized, this would be a suboptimal behavior. So they actually coupled those two problems. If the path planning algorithms wouldn't guide the robot that close to obstacles, a small delocalization may not be that problematic. And that's actually something that we now want to try to achieve. How can we change the overall procedure, or how can we're actually not changing the procedure, the A-star algorithm itself, we keep it as it is. But how can we change the formulation of the problem that we actually get trajectories which keep some safety distance to the obstacles. The easiest way you could think of is probably just expand the obstacles. So take your map and make all the obstacles 10 centimeters thicker. If you do that, just for the purpose of planning, if the robot was before being guided 1 millimeter next to the obstacle, it would be now guided 10 centimeters plus 1 millimeter close to the obstacle. Where you say, okay, that's a reasonable safety distance, I'll stick with this. I just expand all my obstacles and plan a path in this inflated world. And so the robot will keep a certain safety distance to obstacles. Totally fine, you can do that. That's a very good approach if you have enough clearance in your environment, if you don't have any narrow passages. In most environments, you have door frames, for example, and the door frames are not too large, maybe 80 centimeters wide. And if your robot is 70 centimeters wide, expanding everything by 10 centimeters would actually lead to a planning problem where there would be no path, no way for the robot to actually pass through the doorway. So that's suboptimal. So you don't want to enforce the safety distance, but say, if possible, do it. And we can do this with a trick. And the trick that we are now applying in order to solve this, to kind of expand the obstacles, but don't expand them at a full yes, no as a hard constraint, we can use a convolution of the grid map. So remember, we can add a Gaussian blur, so to say, to our map, to our occupancy grid map, for example. So that means we are basically smoothing the occupancy values in local neighborhoods, something that we commonly do in images, in image processing. So, for example, you take your favorite image processing software, whatever, GIMP, Photoshop, or whatever it is, and you have a filter, it's called Gaussian blur. What it basically does, it takes for every pixel neighboring pixels into account and performs a certain type of smoothing with a certain kernel, basically averaging over the occupancy values. That means if you have values where one value is high and the neighboring value is small, you basically take some of the high probability mass of being occupied and kind of move it into the neighboring cell which had a low probability. So you're increasing the probability, occupancy probability of that cell. And if you then relate your cost to the probability that the cell is occupied, you're basically adding some of the expensive cost or infinitely large cost of the occupied space into the nearby free space. You're basically increasing the cost. So it's cheaper for the robot to go to real free space, which is far away from an obstacle, and just by kind of smearing, so to say, the cost into the neighboring cells just a little bit, the system will actually try to avoid those cells if it can. But if there's no other path, it says, okay, there's no other way, I have to pass through that door frame. So at that position in the door frame, I actually need to be really precise and go directly to the center of the door frame, which is also an effect that smoothing can generate for you, that the robot really wants to pass through the center of the door frame, trying to maximize the distance to the walls. This is a more expensive path. The robot may even slow down or use this information to slow down, to navigate more precisely. But whenever there's enough free space, you will actually drive through the free space. So what we do, we convolve a grid map and perform the A-star planning in this convolved grid map. So just as a small example, basically a 1D cut through a set of grid cells. So you have two cells, 0 and 1, which are occupied, occupancy probability of 1. And those which are next to it have an occupancy probability of 0. They are free cells. This would be kind of basically a clipped grid map, a way of just have 0s and 1 values. And if you kind of perform a Gaussian or a binomial kernel, which is kind of gives you a Gaussian blur basically, and move it over those cells and do two convolutions, then your values, your probability values, your smooth probability values would actually look like this. So those get a little bit lower and those get a little bit higher because you're basically taking probability mass and smearing it into the free space. And if you then would actually perform your planning in this convolved grid map, or maybe you afterwards actually enlarge those values back to 1 because you know they are for sure occupied, you never want to go through, move through those states, then these values over here will actually generate cost, which would like keep the robot here at cell number 4, if it can do. If there would be another obstacle over here, it would actually go exactly through the middle. And that's what the map convolution does for you if you perform planning in a convolved grid map. And this is done through a so-called binomial kernel, which basically means for a cell where you want to perform that smoothing, this cell over here, you say, I take half of the probability value of that cell and a quarter of the left and the right cell, and do this over all rows and all columns for the map, and this basically generates a Gaussian blur. And this is a form of kind of pre-processing that you're doing. You basically perform this convolution, and then you take the maximum operation from this convolved map and the original grid map, and then perform the planning in this modified map, which is also often referred to as A star in a convolved grid map. And this allows you to kind of avoid that the robot goes too close to obstacles if it has the possibility to avoid it given the possible trajectories to the goal. And this is kind of a standard method that is done today in most planning algorithms, that you kind of in this way kind of inflate, or not fully inflate, but kind of smoothly inflate your obstacles in the environment and plan in this type of map. And this leads to navigation behaviors or trajectories which keep a safety distance if possible to obstacles, so you still find trajectories which are close to the optimal trajectory, so they're just slightly longer if at all, but your motion execution is much more reliable because the system is much less likely to bump into an obstacle, taking into account that you could be delocalized or the system doesn't perfectly execute what you want to execute. If you would take uncertain action execution into account properly, you would need to go to a Markov decision process, which is something that we also we'll discuss later on, which is a technique in order to plan under uncertainty, but kind of this convolving a grid map is kind of a quick fix to get a similar behavior with much less computational effort. So it's always valuable to actually take that into account. The second thing I want to talk about here is a short remark on that heuristic. So we have seen that heuristic should always underestimate the true cost. And so the question is, can we actually compute the true cost? Yes, we can compute the true cost for a given configuration, and that's something that Dijkstra's algorithm is doing for us. If you remember, Dijkstra's algorithm computes the cost for every node to reach one goal node. So we start Dijkstra's algorithm from the goal node and expand the whole state space. If we can do this, we can actually get a cost for every cell that is the optimal heuristic. The problem is performing this operation is more expensive than A star itself, or the full, or even the uninformed search itself. So if you plan only once, A star is still the way to go. Use your Euclidean heuristic, everything is good. If you, however, plan more often a path to the same goal location, then it may be worse to invest a little bit efforts into coming up with a good heuristic. And if this is the case, so if you say you're replanning every second, still reaching the same goal location, you just replan in order to avoid if the robot is slightly moved somewhere else, you're still on a good trajectory, or you may change your map a little bit by adding obstacles based on what you see, let's say people walking by, but the underlying planning problem is still very, very similar. Then it makes sense to run a Dijkstra path first in order to compute the optimal heuristic and then plan with that optimal heuristic. And that's something which is very efficient and typically done, and which is something we will also exploit in the remaining part of that course. So with this, you get the optimal heuristic for A star. So this is an example. If this is your goal location, you start your Dijkstra's algorithm from that location, so it expands kind of backwards, and the cost will increase the further you go away, the darker the color, until you will be reaching here costs, states of high cost. And if the environment doesn't change, the only thing that you then need to do is basically gradient descent in this map, and basically A star will then basically reduce to a gradient descent if you have the optimal heuristic being taken into account, because you always expand the right nodes. It's not fully true what I just said. So it's not fully a gradient descent that A star will actually generate, but it's still extremely fast. If you know that you have the optimal heuristic, then you could actually do a gradient descent, assuming that the environment did never change. If you have dynamics around, so people walking by, you may need to change your cost map again. And let's say with a person by, some of the states will get a higher cost, but that's not problematic from the heuristic point of view, because heuristic should underestimate. So you could stick with this Dijkstra heuristic, run A star, and A star would assume there's no obstacle. As soon as it finds an obstacle, it will plan a path around it, put a little bit more computational efforts into this, but then continue with the optimal heuristic. And so that's the way you go for if you take into account that you need to replan more often. In the remaining part of the lecture, I would like to look into high-dimensional state spaces. So what can we do in order to take higher state spaces into account, or high-dimensional spaces, for example, if velocities matter. And I want to take into account that I cannot artificially increase the acceleration or the speed of my robot by putting very high acceleration in, that this is a smooth process that I need to do. What we can do is we can still use A-star planning, let's say a 5-dimensional state space planning, taking velocities and changing velocities into account. How would that work? So what we can do is we just say we don't only plan in the X and Y space, as we did so far if we plan in the grid map. We actually plan in X, Y, orientation theta, translation velocity, and rotation velocity, so a 5-dimensional state space, and plan in this 5-dimensional state space. So that means the velocities that we are setting basically in the current configuration tell us what our neighboring configuration would actually look like. So by taking this information into account, we are getting the neighboring states automatically in here. And so now the only problem is we probably can't discretize this state space fully, because moving from a 2-dimensional state space to a 5-dimensional state space, considering that the number of states would grow exponentially with the number of dimensions that I add, this will lead to a substantially larger planning problem, something that is larger than what I can typically handle very well. And that's a problem that I have. So this state space gets actually huge. If I would, however, be able to plan in this configuration, it would be great, because I would have a planning problem which generates trajectories where the fastest trajectory is better taken into account, because I'm explicitly taking, for example, also the rotations properly into account, which is not necessarily the case if I've just planned on a 2D grid map. And I can take velocity constraints into account, or changes in velocities. So I can say, for example, I don't want to change the velocity dramatically. I just have a certain acceleration that bounds the change in velocities, which generates smooth starting and stopping behaviors for the robot. Or which can say in certain areas I want to drive more slowly, in others I want to drive faster. I can just take that in the planning process already into account in order to come up with the optimal trajectory that I'm going to estimate. Okay, so how does it look like? The state space is now this 5-dimensional state space, and in order to go from state number 1 into state number 2, the velocities actually matter. So to go from here to here, so from one 5D state to another 5D state, I may be able to do this if they are nearby and the velocities and the orientation are compatible. So computing those neighbors gets more complicated, because I need to take the physical constraints of the platform into account. But I can, for example, say I have constraints in the acceleration, in the rotational part, in the translational part, how fast I can want to stop or slow down the robot. This can be perfectly taken into account. And so based on the velocities constraints that I set, I actually get out the new configuration of my state. The problem that I have is that I typically need to execute that planning system frequently. So if I don't have an additional underlying obstacle avoidance system running, I need to execute that at high frequencies, 10 Hertz or maybe 5 Hertz for depending how fast my robot actually goes. So if you do indoor navigation, maybe 5 Hertz are fine. If the robot goes a little bit faster than walking speed, you need to increase it to 10 Hertz. If you're driving outdoors on a road, you really need to bump it up to whatever, 30 Hertz, 40 Hertz maybe. So that's the problem. You can't run that planner that quickly in this 5-dimensional state space, because the number of states that you need to explore is simply too large. You need to restrict the search in the state space down. So what you can do is you can restrict your state space in order to just explore a part of the state space and take those states into account which are most likely to be good states. And for this, we can actually come up with a hierarchical way of planning. So the algorithm works the following. We start with our occupancy grid map, and we use sensor information in order to update our grid map. That means if we see an obstacle, we just add it to our grid map. So we have a grid map with my standard grid map, which contains only the static part of the world, the one which is given to me. And basically I have a second map where I'm just adding what I'm seeing. And the map I use for planning is basically the maximum of those two maps. And of course I do the trick with the convolution itself. And then I plan an A star in the standard 2-dimensional grid world. So I just do a 2D planning using this optimal heuristic and all the tricks that I just explained before. So I come up with a trajectory in the 2D world. And then I make the assumption basically, the path that I plan in the 2D world and the path that I plan in the 5D world shouldn't be substantially different from the XY position point of view. So I may deviate a bit from the path, taking the accelerations into account or how I drive on a curve, but I shouldn't change the trajectory dramatically. And therefore, what we can do is we can build up the 5-dimensional configuration space only around the trajectory that I planned in this 2D world, around this XY space. So I kind of restrict the states that I'm actually expanding towards a 5D configuration space. So I'm basically building a small channel in this 5-dimensional configuration space and only build that 5-dimensional configuration space explicitly in this small channel around the path computed in the 2D world. And then do the optimal planning in that channel in my 5D space, but don't need to expand the full search space for this 5D space. And that's something that you can do. So let's go through these individual steps. So I start with using my occupancy grid map, this one over here, my static world. I convolve it, so you can see it on this black values here around obstacles. This is the result of the convolution. And if I detect, or I see some obstacles, for example, from my laser scanner in the environment, I can add that to the map. And I can add it, and what I do in practice, I basically have two maps, one map which never changes, and then a dynamic map which just contains those dynamic obstacles. So thing that I right now see, and I get that from my sensor on a high frequency, let's say 10 Hertz, and can, with 10 Hertz, update that map and take the dynamics into account. So that's kind of the first step. And then I perform my planning in my two-dimensional state space. So I take that map and plan a path in this two-dimensional map. So for example, if my goal is over here, my current location is over here, that's a valid 2D path which guides the robot from the current location to the goal location. And here, basically, keeping this distance to obstacle is a result of the smoothing. And I can do this with using this as the optimal heuristic in order to be as fast as possible in planning and don't expand too many states I actually don't want to visit. And for that, this Dijkstra-based heuristic is valuable because I'm executing that now, 5 times per second. So I'm doing this really, really often, and I want to do as many pre-computations as possible for my heuristic to be as close as possible to the optimal heuristic in order to be able to run this A-star algorithm fast. That means I first need to do this computation. So once I invest maybe half a second of computational resources in order to come up with the optimal heuristic, but then this thing gets 10, 20, 30 times faster than the original planning algorithm. It gets blazingly fast if you have the optimal heuristic. Okay, and then I'm kind of building up my restricted 5D space. Again, I'm making the assumption here that I'm building this 5D space only around the 2D path, and this makes an assumption that the shortest path and the fastest path are not too different. So if I have one path which is short but makes a lot of stops and turns, and one which is slightly longer but a very nice straight line or curved line, then this may not lead to a very good solution because the 2D path will actually take this small detoured path where the robot actually will drive very slowly compared to the slightly longer trajectory. And so if those trajectories are far apart in the XY space, then you won't find them and take them into account. But this happens very, very rarely in reality. So what we're doing here, we're taking the XY path that I computed and built this 5D space around this 2D path and basically built up a small channel. So how did that look like? I have again the example I had before. So this was my path, my 2D path to the goal, and I'm building up that channel, and don't even build up that channel fully to the goal, only up to a sub-goal, let's say 5 meters or 10 meters ahead of me. I said, I want to reach that point 10 meters ahead of me, and now plan how I can optimally reach that point. Knowing that I will replan anyhow 5 times per second, and within 200 milliseconds, I won't drive this 10 meters to the sub-goal. So I have this blue area, which is shown over here, and just for this blue area, I'm actually building up this 5-dimensional state space, which I now can't visualize further, so you have to stick with this 2D visualization and knowing that for all those blue states, we are actually building up this 5-dimensional configuration space, and then plan A star in this 5-dimensional configuration space. So I'm doing the full planning, and what I'm also taking into account in the heuristic, I'm basically taking the velocities into account, how far it is, so the distance to the goal, but also the cost from Dijkstra's algorithm is taken into account in order to guide the search as fast as possible to that state space, or in this case, to my sub-goal. So it's something that you do in order to be efficient here. So this is the Dijkstra or value iteration is only done in 2D, in this 2D space, not in the 5D space. That's important to note, otherwise it would be too expensive. But then guide the 5D search using, at least for the XY states, the optimal heuristic. So this is an example how that looks like. This is a small video animation So this was just one screenshot, and this shows basically the whole animation, how the system starts over here, navigates around over here. You see the 2D path, and then you will also see how the 5D state is expanded. And you see those dotted white lines. This is actually the trajectory that the robot actually computes in every time step, and this is the actual trajectory that the system executes then. So you can see the curve doesn't have this 45-degree rotations. It really generates a more smoother trajectory towards going to the target location, so that the system then reaches that target location on a trajectory which can actually drive fast, taking account the kinematic constraints. And we can also not just do that here in simulation, we can also do that live and change the environment while the system is navigating in order to come up with an efficient path of the environment. And something that you've shown here, you see this robot driving through the environment. These are unknown obstacles. This is a free space also over here, and then we can actually walk into and kind of obstruct the robot. So the person is standing here, the robot sees it and then navigates around. You can see how this channel is built up for the robot in order to navigate through the environment and then even path through rather narrow doorways and avoid collisions, taking always the optimal controls into account. So this was kind of the robot view, and this here was the internal state of the planner. So I can actually rerun that video again, so you can see how the trajectory is actually built, how new obstacles pop up here. So the garbage bin, which is over here, will pop up in a second over there. And so the planner plans around here until a person occupies that space. So the planner plans around and then navigates through the doorway. And then in this case is able to take the kinematic constraints into account and drive very smoothly through the obstacles. You can also check how much does the size of the channel actually impacts your solution. So the smaller that channel is, this kind of blue area, the further you're away from the optimal solution. So you can see it here. This was the width of 70 centimeters and the length of 1.50 meters. So the subgoal you're taking into account, so something which is very small. Then your solution is maybe 10% worse than the optimal solution. Optimal solution means here planning in the full 5D space, something you can only do offline. But if you make the channel a little bit bigger, like say whatever, the 2.50 meters long and 90 centimeters wide, or even more than 1 meter wide and 5 meters long, then there's actually in most indoor environments no difference to the optimal solution. So it's a very effective means to build up this restricted configuration space in order to come up with trajectories which are optimal or near optimal, although you only have expended a small fraction of the state space, so that you can run that even on, by now, whatever 18-year-old hardware. That was a time when this algorithm was developed. You can actually run that at several times per second, even on very old hardware. So something that modern robotics systems can actually run easily online. So with this, I'm coming to the end of today. So we have introduced planning as a way for finding optimal or near optimal trajectories from a start location to a target location. And for that, we looked into search techniques, uninformed search and informed search techniques, where in practice we always use informed search techniques in robotics, or most of the time. So A* is the gold standard for performing path planning. I may do some tweaks to my maps. I may do some pre-computations with the heuristic in order to get that fast and to allow for effective replanning. But it's the gold standard algorithm in order to plan a path for a robot to go from A to B. And it's an algorithm. This is around since the 1969 approximately, when Niels Nielsen developed A* for Shaky the robot. So it's one of the standard planning algorithms used in robotics, and now, but today, a key tool in AI in order to perform informed search. And there are optimizations for that, for different types of problems, finding heuristics or learning even heuristics in order to not make it a user-defined task. But that's all much more in the field of AI rather than robotics, because we are often living in a Euclidean world where we can quite easily define good heuristics, and therefore this is a standard choice that you want to take into account. You can do this in 2D on a grid map, but you can also expand this with some approximations to higher dimensional spaces in order to take, for example, kinematic constraints into account. Okay, that's it from my side. I hope you've understood how you plan, at least if your system has no serious uncertainty in the motion execution. If this is the case, you need different techniques, but if you can assume your system behaves reasonable, then what we presented here is the way to go. So thank you very much for your attention.